Section 8.7 is primarily about applications of exponential functions and logarithmic functions. In other words, we do mathematical modeling with these functions. And so the two objectives are to solve applied problems involving logarithmic functions and to solve applied problems involving exponential functions. So to begin with, we can state that exponential functions and logarithmic functions can now be added to our library of functions. They can serve as models for many kinds of applications. And so to begin with, let's review some of the graphs. And so in the first graph, we have the exponential function f of x equals a to the bx, or a times e to the kx, with a, b, and k greater than 0. So that determines whether we have an increasing function or a decreasing function, depending whether the exponent is negative. For negative exponents, we have a decreasing exponential function, and when the exponent is positive, we have an increasing exponential function. For the logarithmic function, it can be of the form a plus b times the log base c of x, and c greater than 1. And so these logarithmic functions look about the same, except they may be shifted to left or right or up and down. The first example we're going to use it on is the one on sound levels. And to measure loudness of any particular sound, the decibel scale is used. You may have heard this before. So the loudness in decibels, abbreviated lowercase d capital B, of a sound is given by L equals 10 times the log of I divided by I sub 0, where I is the intensity of the sound in watts per square meter, W per meter squared, and I sub 0 is 10 to the minus 12 watts per square meter. Now, I sub 0 is approximately the intensity of the softest sound that can be heard. So let's use this definition to solve a particular problem. So here's a problem about acoustics. The intensity of sound in normal conversation is about 3.2 times 10 to the minus 6 watts per square meter. How high is the sound levels in decibels? So here's our basic definition. The sound level in decibels equals 10 times the log of I divided by I sub 0. So in this case, I is equal to 3.2 times 10 to the minus 6 watts per square meter. And notice that this is a capital W, and m meter squared is a lowercase m. Therefore, our equation looks like L, the sound level in decibels, is 10 times the log of 3.2 times 10 to the minus 6. And using the laws of exponents, 10 to the minus 6 divided by 10 to the minus 12, this becomes a 10 to the 12s, and 12 minus 6 is equal to 10 to the 6. In other words, 10 to the minus 6 divided by 10 to the minus 12 is equal to 10 to the minus 6 minus negative 12. So that's 10 to the minus 6 plus 12, or 10 to the minus 6. So 10 to the 6 rather. So that's where this 10 to the 6 comes from. So therefore, we have 10 times the log of 3.2 plus the log of 10 to the 6. So now the log of 3.2, well, this is now equal to the log of 3.2 plus the log of 10 to the 6. And the log of 3.2 is approximately equal to 0.5051. And the log of 10 to the 6, base 10, of course, is equal to 6. So that's equal to 6. So 6 plus 0.501 equals 6.5051 times 10. So that's approximately equal to 65 decibels. So the sound level is about 65 decibels. The next example is about audiology. Overexposure to excessive sound levels can diminish one's hearing to the point where the softest sound that is audible is 28 decibels. What is the intensity of such a sound? So here, the problem is the opposite. So we begin with 28, using our basic definition that the loudness, the decimals, is equal to log or 10 times the log of the intensity divided by I sub 0. So here we begin with knowing the loudness of 28 decibels equals 10 times the log of I, which is what we want to know, divided by 10 to the minus 12, the softest sound that can be heard. So dividing both sides by 10, this then is 2.8 equals the log of I minus the log of 10 to the minus 12. And remember, this is base 10, natural logarithms, so that means equal log of I minus 12. Actually minus negative 12. So we have then the log of I equals 2.8 minus 12 or minus 9.2. Now when we raise both sides of the equation to the 10th power, then 10 to the log I equals, well, 10, equals 10 to the minus 9.2, or 10 to the log I is of course equal to I. So the intensity is equal to 10 to the minus 9.2 watts per square meter. Next, we're going to look at chemistry, and the pH in chemistry. The pH of a liquid is defined as pH equals minus the log of H plus, where H plus is a hydrogen ion concentration in moles per liter. Let's apply this to the following problem. The hydrogen ion concentration of freshly brewed coffee is about 1.3 times 10 to the minus 5 moles per liter. Find the corresponding pH. So using the above definition, we can say that the pH of freshly brewed coffee is equal to minus the log of 1.3 times 10 to the minus 5. And when we look up that log, the log of 1.3 times to the minus 5 is approximately minus 4.886. So in other words, a minus times a minus, or double minus rather, is a plus. So in other words, the pH is approximately equal to 4.886. Or we say it's about 4.9. So pH of freshly brewed coffee is approximately 4.9. This, of course, is not true for every cup of every freshly brewed coffee, because different coffees have different pH levels. Acidosis is a particular condition. So when the pH of a patient's blood drops below 7.4, a condition called acidosis sets in. Acidosis can be fatal at a pH level of 7. What would the hydrogen ion concentration of the patient's blood be at that point? So the pH is 7 equals minus the log of the hydrogen ion concentration. So 7 or minus 7, multiplying both sides of the equation by 1 to make that a positive. So then that means when we raise both sides to 10th power, then we get the hydrogen ion concentration level that would be 10 to the minus 7. Raise both sides to 10th power. And so that would be in moles per liter. Next, we're going to look at some applications of exponential functions. And one of them is the compound interest formula. And suppose that $40,000 is invested at 4.3% interest, compounded annually. So here's a compound interest formula, the future value of an investment P, an interest rate of R expressed in decimal format to the T power. Part A is, after what amount of time will there be $250,000 in the account? So here we're asking the question, here we're solving this formula for T. So the future value is to be $250,000 from an investment of $40,000, and the interest rate is 4.3%, and 1 plus 4.3% is 1.043. If we raise it to T power, and then of course we're looking for finding out what T is. So the first thing is we divide both sides by 40,000. So then 1.043 to the T power is equal to 250,000 divided by 40,000, and that's equal to 6.25. 250,000 divided by 40,000, 6.25. Now we're going to take the log on both sides. So the log of 1.043 to the T power is equal to the log of 6.25. And so that's equal to T times the log of 1.043 equals the log of 6.25. So when we divide both sides by the log of 1.043, then T is equal to the log of 6.25 divided by the log of 1.043. And so we look up the numbers for the log of 6.25 divided by the log of 1.043, and that is about 43.5 years. So after 43.5 years, the amount will be $250,000. So that's for the A part. And for the B part, we are asked to find the doubling time. When will that double? So when we start out with the basic equation, A equals P times 1 plus R to the T power, since the amount is supposed to double, that means we want to have 80,000 from an investment of 40,000. 1.043 to the T power, dividing both sides by 40,000, then 80,000 divided by 40,000 is 2, equals 1.043 to the power of t. Now we take the log on both sides. The log of 2 equals the log of 1.043 to the t power. We're switching sides. And remembering that this is equal to t times the log of 1.043 equal to the log of 2. Dividing both sides by the log of 1.043 isolates t. So t is equal to the log of 2 divided by the log of 1.043. So we look up the log of 2 and divide it by the log of 1.043, and that is about 16.5 years. So in other words, 40,000 at that interest rate will double in about 16.5 years. Next, we will be looking at exponential growth models, and an exponential growth model is a function of the form p of t equals p sub 0 e to the kt, where k is greater than 0. And p sub 0 is the population at time 0, and p of t is the population at time t, and k is the exponential growth rate for the situation. The doubling time is the amount of time necessary for the population to double in size. So t is on the horizontal axis, of course. It's the independent variable after all. And so if p sub 0 is here, then this time t would be the time required for the population to double. Let's look at a simple example. Population growth. In 2016, the Luxembourg's population was 0.6 million, and the exponential growth rate was 2.05% per year. A, find the exponential growth function. So here we have p sub 0, 0.6 million, and the growth rate k, 2.05%, so that's 0.0205. So the exponential growth function p of t is equal to 0.6 e to the 0.0205 t, where t is the number of years. The second part asks, what will the population of Luxembourg be in 2040? So the first thing we need to do is we need to determine what t is in this case. So t sub 0, or t equals 0, is 2016. So t, in this example, is then equal to 2040 minus 2016. That means t is equal to 24 in this model. So then we have the population 24 years after t sub 0 at 2016 equals 0.6 e to 0.0205 times 24. So that's 0.6 e to the 0.492. And now we look this up on our scientific calculus. We raise e to the 0.492 power, and that's approximately equal to 0.6 times that number is about 0.981, or we can say approximately 1 million population in 2040. So that's the answer for part B. This is the answer for part A, and this is the answer for part B. Another example of an exponential growth function is when interest is compounded continuously. Suppose that $5,000 is invested and grows to $6,356.25 in 4 years. Find the interest rate and then the exponential growth function. The growth function is p of t equals p sub 0 e to the kt. So that we know that after 4 years the amount is 6,356.25, and we began with 5,000, that's p sub 0, 5,000, e to the k. Now t is equal to the number of years, or 4, so times 4. We divide both sides by 5,000. So dividing both sides by 5,000 is equal to 1.27125 equals to e to the 4k. Now we take the natural log on both sides, so the natural log of 1.27125 equals the natural log of e to the 4k is 4k. So then k is equal to the natural log of 1.27125 divided by 4, and that's equal to 0.24 for natural log of 1.27125 divided by 4, and so that's equal to 0.06 or 6%. So then the growth formula, the growth function is p of t equals 5,000 e to 0.06 t. So that's our answer for A. And for B, the question is, what is P of 1? So when t equals 1. So P of 1 is equal to 5,000 e to the 0.06, and that's equal to 5,309 dollars and 18 cents. So after 1 year, and then P of 2, 5,000 e to the 0.06 times 2, and that's equal to 5,637.48, 5,637.48, and P of 10 is equal to 5,000 e to 0.06 times 10, and that's equal to 9,110 and 59 cents. for part C, what is the doubling time? Again, here's our original function. So the doubling would be, now we want P of t equal to 10,000 equals 5,000 e to 0.06t, e to 0.06t. We divide both sides by 5,000. 10,000 divided by 5,000 is 2, and that's equal to e to the 0.06t. Now, when we take the natural log on both sides, ln of 2 equals ln of e to the 0.06t. So that's equal to 0.06t ln of e, and of course the ln of e is equal to 1. So then we have 0.06t equals the ln of 2 or t equals the natural log of 2 divided by 0.06, and that's approximately equal to 11.525. So we can say the time to double is approximately 11.6 years. So that's for the C part. The doubling time is about 11.6 years. For the next exercise, we're going to look at global mobile data traffic, and the amount of data transferred using mobile devices is expected to increase exponentially from 7.2 exabytes per month in 2016 to 49 exabytes per month in 2021, and 1 exabyte is a billion gigabytes. You're familiar with gigabytes, so 1 billion gigabytes is 1 exabyte. Part A says this, that P of t equals P sub 0 times e to the kt, where P of t is the global mobile data traffic in exabytes per month. T is the number of years after 2016. Then t sub 0 corresponds to 2016, and t equals 5 corresponds to 2021. Use the data points 0, 7.2 and 5,49 to find the exponential growth rate and then the exponential growth function. So if we do a little sketch here, it's t on the horizontal axis and the number of exabytes on the vertical axis, exabytes. Then when t equals 0, it's at 7.2. So the growth function is going to look like this somewhat. And so t equals 0, and when t equals 5, then the growth will be at 49. So this is 5,49, and this point is 0,7.2. So in other words, P sub 0 is equal to 7.2. And so we have P of 5 equals 49 exabytes, and that's equal to 7.2 e to the k times 5. K, t is equal to 5, so e to the k5. We divide both sides by 7.2, and that gives us 6.8055 equals e to the 5k. Then we take the natural log on both sides. 6.8055 equals the natural log of e to the 5k, which is equal to 5k times the natural log of e, and natural log of e, of course, equal to 1. So in other words, we have the equation ln natural log of 6.8055 is equal to 5k. We divide both sides by 5, so k is equal to the natural log of 6.8055 divided by 5 is approximately equal to 0.383547, or approximately 0.384. So then the growth function is p of t equals 7.2 e to the 0.384 times t. So this is the answer for part A. For the B part, to find the mobile data traffic per month in 2019, so that means t of 0 equals 2016, then 2019 t is equal to 3, so p of 3 is equal to 7.2 e to 0.384 times 3, and when we evaluate that, that's about 22.8 exabytes. Then the C question, the part C, assume exponential growth continues at the same rate. Predict the year in which the global mobile data traffic will be 100 exabytes per month. So part C asks, assume exponential growth continues at the same rate. Predict the year in which the global mobile data traffic will be 100 exabytes per month. So part C, look at our exponential growth function, p of t equals 7.2 e to the 0.384 t. P of t is now 100, equals 7.2 e to the 0.384 t, dividing both sides by 7.2 will give us 13.888, continuing, equals e to the 0.384 t. We take the natural log on both sides, 0.88 would be the natural log of e to the 0.384 t, which is equal to 0.384 t times the natural log of e, which is equal to 1. So we just have this expression now. So that we have 0.384 t switching sides is equal to ln of 13.88. And then T, to isolate T, we divide both sides by 0.384. So T is equal to the natural log of 13.888 divided by 0.384. And that's equal to about 6.85. So it's about 7. So 7 years after 2016. So that means 2016 plus 7 is about 2023. In the year 2023. So who wants to know this? Well, obviously, when you look at the information that came from Cisco, to support this kind of data traffic, it takes a lot of infrastructure. And so, of course, there are many companies involved that create the infrastructure that can handle this kind of a traffic. 100 exabytes per month. That is a lot of data traffic. Carbon-14 has a half-life. Carbon-14 has a half-life of 5,750 years. So this will allow us to compute K in this formula, because 0.5 of the original mass equals P sub 0 e to the minus K T. And since K is 5,750, so that's equal to P sub 0 e to the minus 0 e to the minus 5,750 K. So this indicates half-life, half the original mass. So the P sub zeros cancel out. So we have 0.5 equals e to the minus K times 5,750. Then we take the natural log on both sides. And it would be the natural log of e to the minus K times 5,750. Or minus K times 5,750 times the ln of e, which is equal to 1. Therefore, we can solve this equation minus K times 5,750 for K. So K is equal to ln of 0.5 divided by minus 5,750, and that's equal to 0.00012. Remember, the ln of 0.5 is a negative number. Divided by a negative number gives us a positive quotient. So then the growth formula is, or the decay formula rather, is P of t equals P sub 0 e to the minus 0.00012 t. Now, so that's our decay formula for carbon-14. Now we ask that the pollen that lost 38.1% of its carbon-14. So in other words, 100% minus 38.1% is equal to 61.9%, or 0.619. So that's what's left over after a certain period of time, t. In other words, we have the formula 0.619 of p sub 0 equals p sub 0 times e to the minus 0.00012 t. The p sub 0's cancel out, so we have 0.619. What's left over sorry, equals e to the minus 0.00012 t. We take the natural log on both sides, the natural log of 0.619 equals the natural log of e to the minus 0.00012 t, which is equal to minus 0.0001 t times the natural log of e, and the natural log of e is equal to 1. So therefore, t is then equal to the natural log of 0.619 divided by minus 0.00012, and so that's equal to t. So the ratio of the ln of 0.619 divided by minus 0.00012 is then equal to 3,997.08. So you can say about 4,000 years. So that is how carbon dating is actually used. So that's the age of the power. So here's our decay formula, and then we apply the decay formula in this way. What's left over? 0.619 of the original equals the original amount times e to the decay exponent here. Then we take the natural log on both sides, and then we wind up solving for t, and that turns out to be about 4,000 years. So this is the end of section 8.7, and this is also the conclusion of chapter 8.